Hello, my name is Selena Wu, and this is my presentation on magnetic braking with Faraday. Experiment introduction. For this experiment, we will observe the behavior of a magnet falling through a conductive tube of aluminum foil. The magnet we used had a mass of 0.023 kilograms and a magnetic moment of 2.337. The tube was 0.304 meters long, had a foil width of 0.004 meters, and had an inner radius of 0.016 meters. We found from the real-world model that the average time for a magnet to fall through was 1.20 seconds, while the computational model found the average time to be 1.1145 seconds. Observations. We used a conductive aluminum foil tube for this experiment since using a ferrous tube, such as a steel pipe, would cause the magnet to stick to the tube instead of falling through. Additionally, the magnet was originally oriented vertically, but then fell horizontally through the aluminum foil tube before falling vertically again after exiting from the bottom of the tube. We observed the magnet fell slower through the aluminum foil than it would have in regular free fall. Fiscal principles used. We apply the Biot-Savart law to find the magnitude of the magnetic field due to the magnetic dipole. We also use the equation for magnetic flux to find the time derivative of flux through each ring due to the falling magnet. Faraday's law allows us to relate the time derivative of flux to find the induced voltage of the rings of the tube. This induced voltage can then be applied to Ohm's law given the resistivity of the aluminum foil tube to find the current in each ring. Then we apply the magnetic force of the current carrying wire on the falling bar magnet to find the magnitude of the magnetic force on the magnet. We sum that value up with the gravitational force to find the net force on the bar magnet. Lenz's law tells us that the direction of any magnetic field produced by an induced current will be the opposite direction to the change in the original field. And finally, Newton's second law, the momentum principle, allows us to update the velocity and position of the bar magnet as a result of the force on the bar magnet over time. Glow script code. This glow script code is split into 8 steps. Part of the first step is to enter in all of the physical constants and measurements for aluminum foil tubes so that we may create a visual model of the tube, as well as initialize the velocity versus time graph. The second part of step 1 includes entering the properties of the magnet, such as the mass and the magnitude of the dipole, and then creating the visual model of the magnet to fall through the tube and setting the initial conditions at time equals 0 and the initial velocity of the bar magnet equal to 0. For step 2, I wrote a function that can calculate the magnetic field of the bar magnet using the equation shown on the left. Step 3 is the function that applies the equation for magnetic flux to find the derivative of flux with respect to time through each ring due to the falling magnet using the equation on the left. Both functions are called in the next slide, which is a simulation loop that predicts the position and velocity of the bar magnet at time t. This code also implements Ohm's law to find the current in the ring as a result of the relationship with the derivative of flux with respect to time. Next, in steps 5 and 6, we find the force of the magnetic field at each ring and sum of the forces using superposition. We add the sum of the magnetic forces of the gravitational force on the bar magnet in step 7 to find the net force acting upon the bar magnet. Finally, step 8 implements the momentum principle and updates the velocity and position of the bar magnet due to the forces on the bar magnet. The resulting visual model shows the bar magnet falling through the tube, a velocity versus time graph, and then displays the final result that the magnet falls through the tube in 1.145 seconds. Reflection. The red ring represents clockwise motion and the blue ring represents counterclockwise. We use the right-hand rule and Lenz's law to find this, since the magnetic field due to the bar magnet is down and increasing as it falls. The change in flux is also decreasing, and Lenz's law states that the induced current will flow counterclockwise, making the blue ring counterclockwise, and thus the red ring is clockwise. If the magnet was flipped upside down so that the south end of the magnet falls first, the magnetic field due to the magnet would be downward and decreasing. Thus, the magnitude of the force of the magnetic field will decrease, making the magnet fall faster since it will be falling more due to the gravitational force on it. The time in the tube of my real-world model predicted that the bar magnet would take an average of 1.20 seconds to fall through the aluminum foil tube, while the computational model predicted the time would be 1.145 seconds. These values are close to one another, but the computational model may be more accurate by incorporating drag force as an additional force acting upon the bar magnet as it falls. The shape of the velocity versus time plot indicates that the bar magnet was mostly experiencing the force of gravity when it initially began to fall. Then the force of the current carrying wire started to counteract the force of gravity to slow the fall of the magnet. If the resistivity of the conductor was reduced as close as possible to 0, then the current induced by the falling dipole would increase and thereby increase the force of the loop on the falling bar magnet. This would lead to a decrease in the downward net force acting upon the magnet and cause it to fall slower. If holes or slots were cut into the tube, some of the ring currents in the computational model would be incomplete and would not allow for current to flow through. The magnet's behavior would be closer to that of one in freefall then, since it would experience a much lesser force from the current-carrying rings and mostly be acted upon by gravitational force. Finally, we reached the result of the lab that the time it would take for the bar magnet to fall through the aluminum foil tube is 1.145 seconds, as calculated by the computational model.